All right, guys, here we go. Here we go. We are going to try to finish section 10.1. Okay, finish section 10.1. So I'm hoping that you guys can see this. I'll make it as big as I can without losing space on the board. So this is big, okay? This is big. This is a big difference. This is a change. This is one of those changes they made, okay, in the statistics world, which I don't quite get how they make changes like that. They've been doing things one way, and then they decide that they're just going to change it, but it is what it is. You know, who am I to say that they're a whole lot smarter than me? So this is a change, okay? You're going to see some of this stuff in your book, but some of it isn't in your book, and we have to figure out how to deal with it, okay? This is going to be something that's called a pooled proportion, okay? I'm not going to get into the, how it's derived, okay, or, you know, too much into the reasons why it's pooled, okay? But what you need to know is that, first of all, we want to make this visible, okay? You've got to put some stars here. You've got to get some attention in your notes, so when you're going through this and you're studying for the quiz, you're studying for the test, and you're studying for the actual exam, that you know that there's a difference here. This is something that's different, okay? We only pool for Z tests, okay? We do not pool proportions. We don't have proportions. It's a pooled proportion. We don't have proportions when we're dealing with T, okay? And we also don't pool for Z intervals. This is only for Z tests. And it has to do with how we find our standard deviation, okay? And it has this, if you notice, it's got PC, okay? P hat C, okay? It has to do with our two samples, okay? And C is, I think C is there because they didn't want to put PP, so they put PC, which is like combined, okay? And I'm going to show you how to find that. Okay? So we have an example coming up right after this, but this is the formula that you use. You need to use your pooled proportion for your standard deviation, and you also need it in your conditions when you're checking for the normal condition, okay? Really, really important, okay? Whether it'll be in the actual test, I don't know, okay? But I know it's really important. So, this is a change we're going to have to make in our notes too, okay? Because the notes are old, and the notes are something that I've got to go back and take a look at. And I just haven't had time to do that this year. But we're going to do it now. So, when you're doing your notes here, where it says normal, I want you to put PC, 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 and PC. All of those proportions need to be pooled. They need to be combined, okay? The rest of the conditions are similar, right? And again, I'm going to show you how to find those pooled proportions in a second, okay? Independent, the same. So here's our problem. It says, hearing loss. Are teenagers going deaf? I know I am, okay? I'm not a teenager, but I know I'm going deaf. Some of it's selective sometimes, okay? Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 to 2006, 19.5% showed some hearing loss. Does these data, again, awkward, give convincing evidence that the proportion of all teens with hearing loss has increased? State the hypothesis. We are interested in testing. Here we go. So, what are we going to say? What are we going to say for this? What did we talk about? We talked about, we will test, right? We will test. That was our terminology. Ready? We will test. And then we do this, and we come up with our null hypothesis, and we say P1 minus P2 is equal to 0. Okay? We're going to label P1 and P2 in a minute, but your null hypothesis is that there's no change. Your alternate hypothesis is that hearing loss has increased. Okay? Hearing loss has increased. So we would say P1 minus P2, whoops, not equal. That's a mistake. P1 minus P2 is greater than 0. And then we have to label what our P1 and our P2 are. Okay? So P1, okay, is going to be the later of the 2 years. So I just want to verify that before I start writing this down. So P1 is going to be the proportion of hearing loss in 2005 to 2006. And then P2 is the proportion of hearing loss in, what's the other years? 1988 to 1994. Okay? That is a really good state. Okay? A really good state. And I'm going to say under here, we will use alpha equals 0.05. We're going to give them our significance level. We're going to put it in there. We're going to put it in there. All right? That's a really good state. Okay? I'm hoping that we're getting better at that. So we stated the hypotheses. Now we're doing the same thing here. Okay? So we're gonna take this and just include it for the next part. Okay? So when I go over here and I do the rest of my 4 steps, just know this is the state. Okay? Because it's the same problem. It's the same problem. Okay? Why they broke it up in those 2, I'm not sure. Okay? But we have the state done. Now we have to do the plan. So I come over here and we do the plan. Well, what are we doing? We have to name our test, okay? We have a 2-sample Z test for proportions, okay? I'm hoping we're getting better at naming the test as well. So now we have to do random, we have to do normal, we have to do independent. Random, it states the samples were taken random. Okay? The state has to do with the center. It has to do with our p-hats being unbiased estimators. An unbiased estimator is a good estimator. Okay? This is also the most important of your 3 conditions. Now, this is where my pooled proportion comes in. So I've got to take N1 times PC and show that's greater than or equal to 10. N1 times 1 minus PC, show that is greater than or equal to 10. N2 times PC and show that's greater than or equal to 10. And then show N2 times 1 minus P2 is greater than or equal to 10. Don't complain because it's long. It's easy. If you're going to complain when something's hard, okay. I mean, you're a whiner, but okay. Don't complain when it's long. It's just long. It's easy. Okay? We take our time, we make it work. So, what do we say? We said P1 was 2005 to 2006. So somewhere over here, just because it's over there, I need my N1. Well, that's from the N from 2005 to 2006. And that's 1800. So I'm going to take 1800 times this PC, which I haven't figured out yet, and show that's greater than or equal to 10. Well, this is how we do it, baby. All right? Let's watch. I'm going to move my eye, and we're going to do this pooled proportion over here. We're going to find out what PC is. Now, we have to combine those two. It's combined. That's why the C's there. It's combined. But I can't just do this. I can't just take 0.15 plus 0.195 divided by 2 and get that pooled proportion. Get the combined proportion. I want to ask you why. And I want you to think about why. And if you did get this when I'm going over it now, I want you to tell me in class, impress me, and say, you know what, Mr. O, I knew why we couldn't do that. Okay? Think about it. Think about why we can't do that. Why can't I just take those two proportions and add them together? It would make sense to me. If I wanted to find a combined proportion, to me that makes sense. It makes sense to me to do that. It makes sense to add those, okay? But let me tell you the reason why we can't. And the reason why we can't is because we have different sample sizes. So if I'm averaging 10% and 20%, right? You would think the average is going to be in the middle, 15%. However, when the sample sizes are different and you're combining these, we can't just add the proportions. This is what we have to do, okay? We have to take the first one, which is 0.195, and multiply that times my 1800. And that will tell me how many people had hearing loss from 2005 to 2006. So when I do that, let's do that. 0.195 times 1800 is 351. Okay? Now, 0.15 times 3,000. Okay, we'll type that in. 0.15 times 3,000 is 450. So, that tells me how many people have hearing loss. So what I have to do is I have to take 350 plus 351 plus 450 and divide by 4,800. That will give me my pooled proportion. Okay, my pooled proportion, I just did it, ends up being 0.167. 0.167. So what did we do? We took our N1 times, wrong. We took our P1 and multiplied times our N1. And then we took our P2 and multiplied times N2 to find these two numbers. And then those become our numerator, and our denominator is N1 plus N2. So this is the pooled proportion that we use. This is PC, okay? And it's a hat because we're talking about a sample. So when I go over here, it's going to be 1800 times 0.167, and then it's going to be 1800 times 0.833. And we want to show those are both greater than or equal to 10. Well, 1800 times 0.167, I just did that. And that was, no, I didn't do that, I'm sorry, I didn't. Let's do it. 1800 times 0.167 is 300.6, which is greater than or equal to 10. And then 1800 times 0.833, and that's 1499.4. 1499.4, that's greater than or equal to 10. Check, check. We go down here, my N2, that was 3,000 times that pooled proportion of 0.167. 3,000 times that pooled proportion, 1 minus the pooled proportion of 0.833. So I'm going to have 3,000 times 0.167 equals 501. That is greater than or equal to 10. And then 3,000 times 0.833, 2499. that is greater than or equal to 10. So how about that? How about that? We've checked our normal condition. The normal condition is satisfied. Okay? That's how you have to do pool proportions. You only have to do it when you have a z-test. That's it. That's the only time you have to worry about that. So I put down here my independent condition, and we are going to say that 1,800 and 3,000 are less than or equal to 10% of all people who experience hearing loss between, the first one was 2005 to 2006, and 1988 to 1994. Okay? A really good job on the plan. A really, really good job. Okay? So, make sure you have that. If you don't have it, please pause the video. I have to erase it to continue. Okay? I have to erase it to continue. And let's see what we get. We gotta do the do. Do the do. Do. Okay, so what are we finding? Remember that first score we said? We gotta find a z-score. This is a z-test, so we use a z-score for a z-test. All right? So it's gonna be P1 minus P2 hats minus our difference, our mean. And what are we saying? That's gonna be 0 over the pooled proportion over, what is it, 1,800? And the pooled proportion over 3,000. And that's going to give me a z-score. Okay, so I put in some of the values, some of them I didn't. P1 minus P2. P1 was 0.195. So I'm going to have 0.195 minus 0.15, okay? Minus 0 over this. I'm hoping the book did that for me. No, of course not. That would be too easy. I've got to do all the workouts. So, 0.167 times 0.833 over 1,800 and 0.167 times 0.833 over 3,000 and take the square root of that. Let's get to the calculator. Let's finish this before the end of the day. It's a Friday. I'm not staying late today. So, 0.195 minus 0.15 equals 0.045, and that's my top. 0.045. Let's figure out this bottom. 0.167 times 0.833 equals, divided by 1,800 equals, oh boy, decimal point, 0, 1, 2, 3, 4, 0.773, 773, okay? Plus, let's do the other one. 0.167 times 0.833 divided by 3,000, that's going to be even smaller. 0.1234 464 plus 0.1234 773, square root of that mess, 0.123 1237 gives me 0.011. 0.045. I got a big z-score here. I can feel it. 0.045 divided by 0.011. 4.09 for a z-score. What do we think of that? What do we think of that? I'll tell you what I think of that. It's pretty big. That's what I think of that. Okay? So we're going to do norm CDF 4.09999. Okay, that's my z to the left, that's my z to the right. We're going to say that this is going to be approximately, probably 0. I think they usually say that for this, with a z-score that big. Let's see if they give me one. Yeah, they just say approximately 0. Okay, so let's do our conclude. With a Pete ready, just listen, okay?